Welcome to Study with me, and today we're going to talk about differentiation. And basically, I'm going to teach you how to find the derivative of a function. So first, let's review something. Let's do a quick revision. So we have f prime x, which is the derivative of a function fx, is equal to the limit of fx plus h minus fx over h when h is a value that is really close to 0, which is, like h is really small. And so here, let's take a look at a graph. So here we have the graph of fx. So I'm going to draw the function fx, right? And here at this point, I'm going to call it a fa. Yeah. And here I'm going to draw a tangent line. Oops. So this is like a tangent line. So we will have the slope of a tangent line, mt, is going to equal to fx prime, right? Because it is going to equal to the limit of fx plus h minus fx over h. And why is that? So here we have the slope of a tangent line at x equal 8, right? Is going to equal here. So here I have my point A here, and then I have a point A plus h, right? So this is h, because h is like really small. So basically, I can just pretend that both of these points belong to this line, and to find the slope of a line, right? To find the slope of a line, right? Determine this value, you just gotta take, so this is x1, y1, this x2, y2. To determine the slope, you will take 2 over y1 over x2 over x1, right? And here we're going to do the same thing. We're going to take this over this. So this will be equal to h, right? So basically, this is the slope of it. But remember that it's only right. It's only right when this value is being close to 0. So that's why we're going to rewrite it as limit. I'm going to write down here for more spaces. The limit when h approaches 0 of fa plus h plus fa over h, right? Or we can write it as the limit when x approaches a, x is equal e plus h, okay? fx minus fa over x minus a. So that's like the definition of it. So this is what a derivative of function looks like. Okay, so there are sometimes a function cannot be differentiable, which means you cannot determine the slope of the function. So for instance, I'm going to draw some of the cases. First, I have a function like this. So this is fx here, so at a, x is y, so at x equal to a, you're gonna see that it's not differentiable, right? Because f is discontinuous. Okay, and even there are some other cases when the graph look like this. So here is what we call a cusp, and also when it has a vertical tangent, right? So you cannot determine the slope, right? And even when the graph has like a corner like this. So in all these cases, the function fx is not differentiable. Therefore, you cannot determine the derivatives of the function at these points, right? These special points. Right? Because simply they just exist. Okay. So, you can use the definition of derivative to determine the derivative of a function, but that would be a little bit long. So mathematicians have invented something easier for us. So for algebraic functions, we have a tool. So basically we have derivative c. C is a constant. Is equal to 0. The derivatives of x to the power of n is going to be n x to the power of n minus 1. And the derivative of c x to the power of n is equal to c n x to the power of n minus 1. So this is what it is for algebraic functions. And let's take a look at an example. So I have fx equal to 2x to the power of 3, and applying this, we will have 2 multiplied 3x to the power of 2, right? So that would be 6x to the power of 2. And let's take another example. If y equal to 1 over x to the power of 2, so we can rewrite it as x to the power of minus 2. So we have the derivative is equal to, let's bring it this down here, x minus 2 minus 1. So that is going to be 2x to the power of minus 3, and we can rewrite it as something like this. So this is but take a look at it. at this. If they want you to find dy over dx, let's say at x equals 0, and you see that if you throw 0 in here, it just simply does not exist, right? Does not exist. So we can say that y is in let's say differentiable at x equals 0, right? So that's for algebraic functions. That's like really easy. And now let's take a look at some rules. So first, let's take a look at the sum rule. Right? This rule will help us to basically find the derivatives of any type of functions that you like almost every type of algebraic function. So first, let's look at the sum rule. So basically, and you can call it the sum and difference rules, because basically it's just that. So let's say we have to find the derivative of a function u, the function v, right? So it's going to be real easy. So that's just going to be the sum of the difference of the derivatives of each function, right? So let's take a look. So let's take an example. Y equal to 3 plus x. And that's going to be really easy. We want to have dy over dx equal to 3 plus 2, which means 6x plus 2. Right? Easy, right? This is like the easiest part. Okay, and we also have the product rule, which basically states the derivative of a function u multiplied by the function v is equal to v multiplied with the derivative of function u and this. We can also rewrite it as this form for short. So let's take an example. If y equal to 3x minus 5, x to the power of 4 plus 8x minus 1, so dy over dx is going to be, so first let's call this part u and this part v, and you're going to have this, right? And 3x minus 5, 4x to the power of 3, right? Plus, so this is like the sum rule, 8, and plus the function. Oh, I'm sorry. That's a minor mistake. That's a big mistake right here. Here we're going to 3 and multiply with this part. And now we're going to so this is basically how to do it. And well, you can write like the full form of this equation, but I ran out of space, so basically that's it. Okay. Now let's take a look at the quotient rule. Basically, u over v, everything prime, and that will equal this. So this, you gotta memorize this. Let's see that here we have u is at the numerator, so you will have to differentiate it first to put it here and take the positive. Just basically you want to minus it. You have to minus the derivatives of the denominator. You put that in the second place. And this part you actually have to memorize it. So let's start. So I'm going to, oh wait, a minute. So here I'm going to help you guys. Let's take a look at an example. Let's say fx equal to 2x minus 1 over x plus 5. And I'm going to let u be 2x minus 1, then u prime x would be 2, right? Let's v be x plus 5, then v prime x is equal to 1, obviously. So we have fx prime is going to be u prime multiply it by v minus v prime multiplied by u over v to the power of 2, and we're going to have 2 x plus 5 minus 1, 2x minus 1, x plus 5, so it's going to be 2x plus 10 minus 2x plus 2, it's going to equal 12 over x plus 5 to the power of 2. That's it. This is my final results. So it's like some rules that you have to remember, right? This is sum or difference rule. And now you guys can take a screenshot. Okay. So next we're going to talk about the chain rule. The chain rule. So basically, finding the derivative of a function. It's like taking apart an onion, because, well, if you have a function like this, how would you do? Let's take a look at this function. So here we're going to have to treat this like two different functions. So first, function of x equal to x to the power of 10, right? Next is the function gx, which is equal to 3x minus 5. So we're going to have to treat these like, so basically, when we have y equal to f u and u equal to gx, then let's make sure that these functions are differentiable, then we're going to have dy over dx equal to dy over du over dx. So basically, y prime with respect to u multiply with u prime, right? So here, we're going to apply that to our little example. So here, I'm going to just do that. Let's say this is u, right? This is u. Let u be 3x minus 5. Then we're going to have dy over dx equal to du over. So first dy over du, right? That'll be 10, right? Multiply with u to the power of 9, right? 10 minus 1 equals 9. And now we're going to keep on multiplying. We're going to multiply with du over dx, which is 3. So basically, we're going to have 3x minus 5 to the power of 9. And this is our result. So let's take another example. We have y equal to 5x multiply with the square root of 25 minus x to the power of 2. And now let's find dy over dx. So here, I'm going to rewrite this like this, right? So writing this form, that would be much easier for me. And now I'm going to treat these two as different functions. So this is u and this is v. So first we're going to have to see that we're going to have to apply the product rule first, right? So let's take a look at it. So I'm going to have dy over dx is equal to du over dx multiply it with v, right, plus dv over dx multiply it with u. And now I'm going to rewrite it as 25 minus x to the power of 2 to the power of 1 over 2 plus, oh my gosh, and now we're going to have to determine dv over dx. And here we're going to treat as two different functions, right? So first 1.2 I mean 1 over 2 0.5 plus keeping the thing inside the bracket, and now minus 1. And here we're going to have to continue to differentiate the thing inside it. So it's going to be minus 2, right? X minus 2x. Now we're going to keep multiplying. I ran out of space. Multiplying with u, which is 5x. So when we rewrite this function, when we rewrite this equation, it's going to be 5 25 minus x to the power of 2 minus 5 over 5x to the power of 2, and everything here we're going to divide it with respect to 25 minus x to the power of 2 to the power of 1/2, and that's it. And we can even simplify it. I really ran out of space. Okay. So this is our final result. This is our final result. I kind of ran out of space, but here you can take a look at it. Okay, so that's basically the application of the chain rule. I'm going to take another example for you guys. But I think that we kind of... Okay, I'm going to take another example. We have y equal to 2x minus 1 for x to the power 2 to the power of 3, and now let's find dy over dx. So here we're going to apply the quotient rule, right? So let u be 2x minus 1, then u prime x would be 2, plus v be x to the power 2, then v prime would be 2x. And here we're going to apply the chain rule. dy over dx is going to be 3, the whole thing here, right? Alright, and now we're going to have to multiply it with the derivative of this whole thing. So that's going to be u prime v minus v prime u over v to the power of 2, right? So that's going to be u prime is 2v, right, minus v prime u over, let's say, here, and now it's going to be put inside. I'm going to rewrite it as here 4 1 over x 4 and here you're going to have this 2 minus 4 minus 2 x it's like 12. What else? It's like okay. Wait, where's my eraser? And we can easily divide this with respect to x, right? But I'm going to do it right now, right here. Oh, shit, we ran out of space again. So, basically, it's going to... Here I'm going to divide that with respect to x. I'm going to put 2 outside of the equation, and we're going to put 3 outside too. So it's going to be 6 here, and here that would be 1 minus x. 1 minus x. And in here it's going to be, oops, 4, 4, 1. 4, 4, 1. So that's basically this, and you can see that that's basically equal to 2x minus 1 to the power of 2. So this is like our final result after simplifying. That's it. So next, let's talk about trigonometric function. And you know, their inverse counterparts and exponential. Okay, we're gonna talk about exponential and logarithmic functions later, but now let's talk about trigonometric functions first. So basically, just remember that derivatives of sine x is equal to cos x, and the derivatives of cos x is sine x, but make sure to add a minus. Make sure to add a minus sine. Next, how about tan x? Tangent x. It's going to be 1 over cos x to the power of 2, and we can rewrite this as second x to the power of 2. And the same thing so here we have sec x, tan x. Okay, first, so because I want to present to you guys like some kind of a pattern, so I'm going to group these 3 functions together. Let's put it here. Okay. And now, in here we're going to take a look at these functions. The dx of cos x, cosine x, equal to minus sine x. D over dx of cotangent x, right, equal to minus cosecant x, right? And now d over dx of cosecant x is equal to minus, you know, just like the same pattern that we're seeing here, we're like with a minus sign symbol, so it's going to be cosecant x multiplied with cotangent x. That's basically it. And so there's like a tip to remember that the derivatives of cosine, cotangent, and cosecant all have a negative sign. So you can just remember because of the C at the beginning, right? That's like a memorizing tips. So let's take a look at an example. We have y over equal to 6x here we have this function, and now we're going to find dy over dx. So we're going to apply the sum rule, right? So for the first part, it's really easy. It's going to be 12x. And now here we have this coefficient. We're going to keep it here. And now the derivatives of secant x is equal to secant x, right? Multiply with tangent x. And here we go. This is our derivatives of trigonometric function. And now, let's say we're going to have to apply the chain rule. So let's take a look at this example. So fx is equal to cotangent x. Cotangent for x minus 6. So here we're going to apply the chain rule. So first, the derivatives of cotangent would be minus, right? Remember the minus sign, negative sign, because it's cotangent at c at the top, and obviously it's be the cosecant, right? Of 4x minus 6, and now we're going to have to multiply with the derivative of 4x minus 6, which is equal to 4. So it's going to be 4 cosecant to the power of 2 of 4x minus 6. And here, and we can even rewrite that as minus 4 over sine 4x minus 6 to the power of 2. So this is how we're going to tackle trigonometric functions. And now, there's something that's tricky coming up. Okay, now we're going to talk about inverse trigonometric functions. And here, I'm going to show you guys a tip to memorize all of these derivatives of the functions. So we're going to consider d inverse sine u over du, and the same thing for tangent, inverse tangent, and inverse secant u. Okay, so let's memorize at this one. Secant u is like an oddball, like it's a little bit different from what I say. But first, let's write the numerator first, and so for all of these functions, the derivatives will be a fraction, and therefore the numerator is 1. Okay, next we're going to see here that sine u and secant u both have 2s, so that's like we know that there is the square root involved. So that's why I'm going to draw a square root here, a square root here, just like that. Okay, and let's say, and you see that for tangent u, you see this letter T, right? That looks like an at sign, so it's gonna be a plus sign, and because for this one a plus sign, so for these two functions that would be a minus sign, right? Okay, and now we're going to fill our number in, and we're going to fill 1 and then u for these two functions, and this one is odd, so it's going to be u and then 1. So just look at this. See, here's 1 minus u to the power of 2. For this one, it'll be 1, then u to the power of 2. This one is an oddball, so I'm going to write u to the power of 2 and then 1. And for this, we're going to add u here too, and make sure to take its absolute value, and here, so And as you can see that in order for this to be defined, we need the absolute value of u smaller than 1. And the same thing, not the same thing, but the opposite thing happens to this side here. And that's how I remember it. Okay, so how about cosine, cotangent, and cosecant? We only need to add a minus sign for those functions, right? So let's say for cosine, the only thing we need to do is to add a minus sign. For this one, let's say cotangent u, add a minus sign, and for cosecant, I'm going to add a minus sign, and it's just that easy. Okay, so that's how we memorize it, and now let's take a look at an example. So I have y equal to 5 inverse sine 3x. And now let's find dy over dx. So first we're going to multiply with 5, right? And now we'll treat this as a combined function. And so for inverse sine x, that's going to be, the numerator is going to be 1, right? And there is an s, so there is a square root involved. And it's going to be a minus sign, and we're going to fill 1 and then u to the power of 2. And here our u is 3x, right? To the power of 2. And now we're going to multiply with the derivative of 3x, which is 3. And that will give us 15 over the square root of 1 minus 9x to the power of 2. So this is how we deal with inverse trigonometric functions. Let's take a look at another example. Okay, so we have y equal to inverse cosine 1 over x. And now we're gonna let u be 1 over x, and we can rewrite it as x to the power of minus 1, and it's going to be, take minus 1 down here. It's 1 x to the power is minus 2. So we obtain something like this. And now, this du over dx. Okay, so here we're going to have dy over dx. So it will be dy over d2 multiplied with du over dx. And dy over du, because this is inverse cosine, right? So you see the c here. So for cosine, obviously we need a minus sign first. And now, for cosine, you see an s here. There is a square root involved in cosine. You remember, right? Here is a minus sign, and we're going to fill 1 and then u to the power of 2. And u to the power of 2, which means 1 over x to the power of 2. And now we're going to multiply with du over dx, which is minus 1 x to the power of 2. And now 2 negative will be positive, and that will leave us with something like this. 1 here, and now I'm considering putting an x inside here. Oops, this inside the square root would give us something like this. So obviously, right. So this is our final results. And now, if you want to understand this part, let me rewrite it for you. Okay, so we can rewrite this. Rewrite this part here as right. I'm gonna take a square root of this, right? And so it can be written like this. And you know that they're gonna take like the positive value here. So we got this divided by this would equal to this guy. So that's why I really like that. That's why there is an absolute value sign there. Okay, so that's all about trigonometric functions and inverse trigonometric function. And now let's take a look at other kinds of functions as well. So we got exponential and logarithmic functions. Okay, so I'm gonna take a look. Let's say d e to the power of x. Let's take a derivative of e to the power of x. And really, for this one is really easy, like you don't even have to change anything at all. That'd be e to the power of x. Next, d of that would be equal to 1 over x. Easy, right? So, and we notice that, so for this symbol is actually log ex, right? So you can see that because this value is larger than 0, so this guy should be larger than 0 too. So here we have d or dx of a value to the power of x. Then first we're going to write similar to this. We're going to write a to the power of x. However, we're going to need to multiply it with log e a, right? And make sure that a is larger than 0 and a is not 1. It's different from 1. Why is that? Because we're going to treat a as a function here, a function of e here. So that's why we need to multiply it with this. And the same kind of apply to the function log a u. It's going to be here, it's going to be a fraction, right? The numerator is the same, but for the denominator, we're going to, I'm sorry, I don't know why I keep messing up with u and x. Okay, now we're going to do pretty much like the same thing here. So we're going to put x here. However, just like in this case, we need to multiply it with log EA. And that's basically it. And we still have to apply the same condition in order for our equation to be definite. And now we're going to take a look at a few examples. You guys can take a screenshot if you like. Now, let's take a look at an example. Y equal to x e to the power of x minus x to the power of 2 e to the power of x. And first, for this one, so we're gonna apply the product rule, right? This one's gonna be a 1 multiplied with e to the power of x plus x to the derivative of this will still be e to the power of x. Now we're gonna minus the derivative is this one would be 2x e to the power of x plus e to the power of x. And now here we're going to kind of just like rewrite it like this, and now we see which one can be simplified. It's going to be x to the power of 2 with e to the power of x minus x e to the power of x and plus e to the power of x, and we can take we're going to factor e to the power of x, and that will leave us with e to the power of x. Oops, sorry. No, we cannot. We don't have anything after this here. I kind of like forgot the minus sign. So this is our final results. This is a minus sign, guys. Okay, let's take a look at another example. I'm gonna change the color just because I want to. Y equal to 3 to the power of sine x. And now we're going to, first, let's take a derivative. I'm gonna let u equal to sine x. So du over dx would be cosine x, right? So now dy over dx would be dy over du multiplied with u over dx, and dy over du would be, first we're going to take 3 to the power of u, right? And now we have to multiply with this, and next we're going to multiply with u over dx, and that would be cosine x. And I'm going to rewrite it like this: sine x put sine x in here, and this is cosine x. And oh, I'm sorry, my mistake. That's actually 3 in here, right? Yeah, because our formula. No, I'm just trying to challenge you guys. Like, if you guys had noticed my mistake, because our formula is like a thing that is different from. Okay, first, so let's revise. We have a over x versus, a to the power of x versus e to the power of x, right? The thing that's different here is a and e. So the thing we have to multiply is the logarithm of e, a, right? So that means this. Like this is what we have to multiply with. It's not u, it's a. Right? That's a problem we want to fix. Sorry, that's my mistake. Okay, let's add some bracket to avoid any further confusion. Okay. And now let's take a look at another example. because I kind of messed up. Okay, y equal to x to the power of 2 plus 2x minus 3 plus 5. Okay, here it's going to be really easy. First, we're gonna let this be u, right? So we're gonna write a fraction, and now we're going to multiply with the derivative of this polynomial expression. That would be 2x plus 2, right? And now, because this is actually a constant, so we don't need to add anything. So that will leave us with this expression. And this is what we need to find. Okay, let's see. Another example. So here we have y equal to log 5 2x plus 1. Here we're going to do pretty much the same thing. We're going to write a fraction first. We need to put 2x plus 1 here, and now we're going to need to multiply with 5, right? And now we're going to need to multiply with du over dx. With this one is our u, so we multiply with du over dx. So du over dx would be 2, and that will leave us with 2 over 2x plus 1. Okay, so this is our final result. So that's pretty much everything for today. We've revised on the topic of differentiation with all kind of functions. Not all, but most popular and common that you will find on the AP calculus test. And so, yeah, this is the end of the video. Make sure to subscribe to my channel for more videos like this. Thank you and goodbye.